For this last video, we're going to talk about estimating series, and the real idea here is once you know a series converges, so if I have a series like this, the sum as k goes from 1 to infinity of ak converges, I have a question, and that is, what does it converge to? Well, the simple answer is you just shove a whole bunch of points in the series and see what it converges to. But sometimes they converge rather slow, and it's nice to know, do I need to put 10 points into the series or 10,000 points into the series or 10 million? And if I put 10,000, is that close or how close it is? So the real question is once it converges, suppose I do ak from 1 to capital N of ak, how close is that to whatever my real limit is? So suppose I want to put this less than L, then how does that compare to my real limit? And so importantly, the way we're going to do this is I'm going to think of that, and then we're going to add the rest of these terms. The k goes from capital N plus 1 to infinity of ak. And this is going to be the part that we're going to evaluate. So this is the part that we compute. And then this part over here is the error. And the book didn't say anything about the error, but I kind of like giving this a name. So let's call this E capital N. And notice we'll start at N plus 1 because this is E capital N, so this is the error after computing capital N terms. Okay, and so what our real goal is to estimate this error. And so what we would like to do is have some sense of can we estimate what the error is. And importantly, like for example, if we could say that we know the error is between some collection of values, alpha and beta, then all of a sudden we're in really good shape, because if those two values are really small, then we kind of know what the error is. I guess we also, if the error is just less than beta, then that's great because we can just make beta small. Okay, so the big idea here is, as I just said, it's just the idea of estimating this error term. Now, just so you know, I'm going to do this a little bit different than the book. I'm going to use a little bit different notation, and for two of the problems at least, the formula I come up with is going to look on the surface quite a bit different from the one that you see in the book. And if you want to read the one in the book and you like it better, don't hesitate using it instead. But I think these make more sense and are worded in a way that makes more sense to us. Okay. I'm not going to go back through the proofs, but at the heart of each of these, we're kind of looking at the proof and seeing how the proof was used to tell us why the series converged. So if our sequence of AK converges by the interval test, by the integral test, I said the word interval. If the sequence converges by the integral test, then what did we know? Well, the way we came up with this was we drew ourselves a picture where we had 1, 2, 3, 4, and then I took the height of my sequence, like A1, and put it like that, and then A2, and drew a picture like that, and A3, and drew a picture like that, and then I just kept drawing my picture. And then what I did was I compared it to a sequence that looks like this, to a function that goes through all those points. So we had some point that hits all of those values, and then we compared it to those values. And you notice that the value underneath the integral is somehow comparable to the value over the integral. And importantly, right, we could have drawn these black values backwards to make them go. But the important idea was that we had, well, the integral from 1 to infinity of f of x dx is less than or equal to this sum as k goes from 1 to infinity of ak. But it also was greater than the sum if we started 1 ahead. So the k from 2 to infinity of ak. By the way, here our ak is the same as putting k into the function is the same as putting that x in that function. So we're assuming that this function f and this a are the same thing. Okay, so let's just come and think about this. By the way, this second inequality, if we're still thinking about this, this inequality right here, it would be just by drawing all of my rectangles in the backwards direction. And then I would get that those are all smaller than my integral. So if I start at 2, then I get a value that's less than my integral. And if I start at 1, then I get a value that's greater than my integral. Okay, well, let's just take this idea and now expand it. But this time I want to ask, well, what's that error term going to be? And the way I'm going to do that is I'm just going to draw the same picture that I had before. And we'll draw a bunch of these blocks right here. And tell you what, I'll go ahead and draw that function on here. And so our function is going to look something like that. And then somewhere down the road, we'll hit our point that looks like this. And this will be capital N. So this will be our N point. And what you see is that the exact same relationship that proved our theorem before says that the error for this term, which is the error for this term, which, by the way, the error starts at n plus 1. So the error is all of these. So notice that error term has to be less than or equal to the integral from n, greater than or equal to. Let me just erase this and give myself a little more space. So that n error, it's going to have to be greater than or equal to this blue area to the right. So you notice if I take the integral all the way over here, it's going to be greater than that. So it's greater than the integral from n plus 1 to infinity of f of x dx. But now it's also less than, if I just add a little bit of area, I could add this area here. So it's going to be less than that integral right there. And you'll notice that that if I flip all of my terms around, I'll be dealing with the one less version. So that means it's somehow between the integral from capital N to infinity of f of x and the integral from capital N plus 1 to f of x dx. So this is how we can kind of estimate this area. By the way, sometimes you might want to subtract these from each other. So you might want to subtract the n plus 1 from all the sides, and then this becomes just the integral from n to n plus 1. And that technique is a lot more similar to what the book wrote. But that seems to get a little confusing to me. So let's just do a quick example. So suppose I wanted to do something like the sum of 1 over x, natural log of x. Then what might I do? Tell you what, natural log of x squared. Then what I might do is I might compare this with the integral test, and I might do the integral from 1 to infinity of 1 over x, natural log of x squared. I guess these probably should have been k's over here, but we can make them x's for now because why not? By the way, we don't want to start at 1 because the natural log of x is 1, so we want to start at 2 dx. And then what am I going to do? I'm going to let u equal the natural log of x, and then du is 1 over x dx. And so this integral becomes the integral of 1 over u. And we want to go from 2 because that one started at 2. Becomes the integral of 1 over u squared du from the natural log of 2 up to infinity, because the natural log of t is infinity, so we'll go the limit as t goes to infinity. And so then this becomes, that's u to the negative 2, so this is going to become negative 1 over u evaluated from the natural log of 2 to t, and then we'll take the limit as t goes to infinity of that. And then as we take the limit as t goes to infinity, we get 1 over the natural log of 2. So that's why that thing converges. But if I wanted to estimate my error, what would I do? Suppose I want to estimate my error. Well, what I might do is instead of starting at 2, I might say take the first 10 terms of this thing. So I might do something like this and say, let's just take the first 10 terms, the sum of 1 over k times the natural log of k squared, and go k from 2 to 10, and then I might just add all these up and I would get some number. But then how close would that number be? Well, I know that that number is less than what I would get if I put 10 in here, which would make this a natural log of 10, which would make this a natural log of 10, and so I know that I'm within, that error now is less than, and so I know my error now is less than 1 over the natural log of 10. And by the way, I also know that my error is going to be greater than 1 over the natural log of 11. So it kind of gives me some picture of just how close that error is. And natural log of 10, natural log of 11 are fairly close to each other. But notice if I got my computer out and cranked out 100 terms here, then I would be in a lot better shape, because then I would be doing natural log of 100 and natural log of 101. This sequence actually converges really slowly, so you'll find you're going to have to go way down the road if you want to get this accurate to 5 or 6 decimal places. But okay, maybe that gives you a little bit of picture. We just change this term on the integral to get a different value here for our term, and that's how we bound our error. So we use our sum, whatever these sums are. We could type this in a calculator or something if we want, and then we know how close those are by comparing the error. Okay, alternating series test. If you remember doing the alternating series test, what we had is we had the sum of negative 1 to the n, a negative 1 to the k, a sub k, as k goes from 1 to infinity. And what we found is that this converges if those a sub k's decrease constantly to 0. And the way we did this is by the proof that we had earlier. We showed that the absolute value of negative 1 to the k, a sub k, the absolute value of the sum, I'm going to have to rewrite that. So if you remember from our proof, what we showed is we showed that that always had to be bigger than 0, but it also had to be less than or equal to whatever that k term is. But this is actually great. Sorry, not to the infinity. This is the nth term. Had to be less than that a k term is. Okay, but then you see we've got our oh no. Okay, okay. We actually did the k goes from n to infinity, and this was less than that nth term here. Sorry about that. I confused myself a little bit for a second. And because what we did was we bounded the tail, and we said, well, the tail part, and we did this by, if you remember, comparing these alternating terms. And so we took every second term and paired them up and showed that they either had to always be positive or always negative, depending on whether the first of the paired term was a positive term or a negative term. And so this is always less than a sub n, but then this is great because this exactly is our error term. So what that means is if I take my sum, once I'm taking my sum, if I have the error term, and by the way, this is the error of the previous term. So probably what I want to do is I want to say that my error term is just equal to a n plus 1. So it's whatever that next term is it's just whatever that next term is on my sequence. So for example, if I'm looking at the sum that we talked about a lot, negative 1 to the k over k, as k goes from 1 to n, well, maybe I want to add a whole bunch of these up. Well, so I might add together k goes from 1 to, I don't know, to 10 of negative 1 to the k over k. And then I have that 10th error term. Well, how big is that 10th error term? Well, we can see right here that the 10th error term is got to be less than whatever that 10th term is in my sequence. So that means, or whatever that 11th term in my sequence, it's less than 1/11th. So by the time I've added 10 of these, I'm within 1/11th of having the actual sum as I go all the way through the problem. Now this is actually converging kind of slowly. So notice if I wanted to get like 3 decimal places, I would need to put 1,000 terms in here to get within 1,000th of my thing. So this is actually converging quite slowly. But if we use enough terms, we can estimate it. Not only that, we have some sense of how accurate our estimate actually is. Okay, finally, we'll talk a little bit about the ratio and the root test. And so the big idea of both of these is that the ratio and the root test was trying to compare our series. And so we were asking, is it converging? Absolutely. And so both times we were comparing that series to a geometric series, x to the k. Right? So this was a sub k as k goes. Both times we were comparing it to a geometric series. And so what we're going to use is we're going to use the fact that we know that a geometric series as k goes from well, we know if it goes from 0 to infinity, then it's 1 over 1 minus x. But it turns out that if we start at a different value, if we start at, say, capital N, then you end up with x to the capital N minus 1 to the 1 minus x. And that's capital N plus minus 1 to the 1 minus x. So wait, no. It needs to be plus 1. Yeah, okay. Yeah. Okay. So that makes sense. Okay. So we're just going to do capital X to the capital N plus 1 over 1 minus x, and that's going to work. That's going to work just fine. Oh wait. Yeah. Okay. So I'm confusing myself again. It's just capital N. Yeah. It's just capital N because it's whatever that first term is. If it was 0, it was x to the 0. If it's 1, it's just an x. Okay. So this is the formula that we're going to use, and then we're just going to go back again and think about the proof. And so if you remember the proof of the ratio, so if you remember about the proof of the ratio test, what I did was we said if n is large enough, then we compared ak plus 1 minus ak was equal to r, and we said, well, that's less than some x, which is less than 1. And so then that meant that ak plus 1 is less than ak times x. And then I probably should have written this. This would have made a lot more sense. So then ak plus n is now less than ak times x to the n. So what you'll notice is that I'm just building these things up so that they're always less than x to the n. Okay, so the big idea with what we can do here is we can just let our capital N be big enough so that our sequence has converged where r is less than r. So what we do is we find n capital N so that for n greater than capital N, that series a n plus 1 over a n, which is less than x, which is less than 1. So find an n which is less than x. Oh, I guess we have to find an n and an x value. So you have to pick your x value first. I think I said equals. I think earlier I said this equals r. It doesn't equal r. It approaches r. It could always be bigger than r. So that equal sign was a false equal sign. Take some points off my paper. That would be great. Okay, so we're going to find an n so that for that value it's bigger than x. As we said earlier, that means that a sub capital N plus little n is always less than a capital N times x to the little n. And so what does that mean? So that means that if we sum from capital N from k if we sum from k equals, say, capital N plus 1 to infinity of a sum capital N of a sub k. So if we're summing a bunch of these things, then basically what we're doing is we're adding all the points after that capital N value, which is large enough, well, then we know that this thing must be less than or equal to the sum as k goes from capital N plus 1 to infinity of a capital N times x to the capital N plus 1 minus little n. Well, okay, so that's a little bit of a mess. Wait, sorry, no, minus k. But then really what we're doing is let's just recoup this k value so that now it's the sum as k goes. So let's make it j instead. So we'll let j go from 1 to infinity, and it'll be a sub capital N of x to the j. And now, and what have I done? Well, I've just let j equal capital N minus k minus capital N. So what's the idea here? I'm just changing the index just so it makes a little bit more sense. Actually, I should probably make it go from 0 to infinity. Let's make it go from 1. That's fine. And so then this is a capital N times x over 1 minus x, because this thing is now converging to x. Okay, so that gives us a nice little formula to go with. So what does that mean? So that tells us something about our error. So it tells us that when we have the ratio test, that error term that we were talking about earlier, the capital N error term is just whatever that nth term is, the absolute value of it, times x over 1 minus x. And so this error term is the error term for the conditional, the sum of the absolute value of a sub n. So it's the error term for the absolute convergence. So we don't know what a sub n converges to, but we know what the absolute values converge to. Okay, the root test is going to be something pretty similar. So the root test, if you remember the proof of the root test, all we did was we picked it large enough so that a sub k to the 1 over k was less than x, which is less than 1. And then we raised everything to the k powers. That meant a to the k was less than x to the k. So all we're going to say is that if we're looking at the error capital N, which is the sum from as k goes from capital N plus 1 to infinity of the absolute value of k, then all this this is going to always be less than or equal to x to the k, which is the sum as k goes from capital N plus 1 to infinity of x to the k, which is just x to the capital N plus 1 over 1 minus x, just using our formula for above. Okay, so what does that mean? So our root and our ratio test just give us a way where we can estimate. So again, you take the first 10 terms, and then this one is that 11th or that 10th term times whatever that x is and whatever that x is, and so you can estimate your values that way. In this one, you don't have to have the term, you just look at the values of x. Okay, I feel like I was rambling a little bit. Again, the formulas in the book are a little bit different, but hopefully this makes a little bit of sense. I would like you to try to do some of these. So I'd like you to try to actually find a few estimates on your own, and I'll give you those tomorrow, and we can do those during the presentation time. There's a couple that are really interesting. So, for example, what is the sum of 1 over k squared? Can you get that estimate to within a couple decimal places? Then there's some others that are quite interesting, like that -1 over k. -1 to the k over k. That one was quite interesting as well. So I'm going to give you a couple of these tomorrow, and you can work on them. So sorry for the rambling. I hope that this is making sense.